Take it away, Anton.
Okay. Good morning, everybody. I'm happy that you were able to join us in this presentation of Hagar Hauzer PhD thesis. Hagar started her master's thesis with me and continued it for a PhD thesis under the supervision of myself and Yair Rosenthal. She did her bachelor's studies in our Department of Geology here, and a master's and PhD in the curriculum for oceanography. And she will explain the main subject she worked on, but I would like to mention that this is a joint project between Yair Rosenthal, David Evans, and myself. And Hagar did a fantastic job on culturing foraminifera, and she will tell you all about it in her presentation. So good luck, Hagar, and go ahead.
Thank you very much. The thesis title is Development of New Foraminiferal Proxies for Paleochemistry of the Oceans. First of all, I want to mention that this project, as Jonathan mentioned, is a collaboration with Yair and Jonathan, and it was funded by both NSF, BSF, and ISF. I want to, first of all, thank my advisors, Jonathan and Yair, for their help and guidance throughout my research. I want to thank my committee, Hagit Afek and Sigal Abramovich. And I want to thank all the people that helped me with my research in the lab or with the data. David Evans, Adam Levy, Matan Yona, Sharon Ram, Shai Oron, Oriya Moav, and Tanya Rivlin. And in addition, I want to thank Sandra and Maggie. The main points we're going to discuss today are a short introduction of the variations in major ions in the seawater, in past seawater. I'm going to introduce a new calibration of sodium to calcium ratio in foraminiferal as a proxy for past calcium concentrations, which I calibrated in laboratory culture experiments in Jonathan's lab. And I will show you an initial application to the fossil record and conclusions. Foraminifera are unicellular marine organisms, and as you can see in the pictures, they vary in size and shapes, and they govern the oceans in every marine environment, from planktonic foraminifera that lives within the water column to benthic foraminifera that lives on top or within the sediment. And most of them precipitate calcitic shells. They are very abundant throughout the fossil record for the past 540 million years, and they are very diverse. There are more than 40,000 species, and that is why they were initially used as biostratigraphy tool. But the main focus for this talk is that they precipitate their calcium carbonate shell directly from seawater, which enables trace elements to be incorporated into the lattice, and then they actually record their environmental conditions and can be used as proxies. Foraminifera can be found in chalks and limestones in the geological record. And here you can see an example of an Egyptian pyramid that contains many nummulites. These are large benthic foraminifera that grew up to be around 20 centimeters in size. We will talk today mainly about proxies. Here we have a list of proxies that are used in foraminifera. On the top here you can see the isotopic proxies, and on the bottom you can see the element to calcium ratio proxies. This is the main focus for this talk, the magnesium to calcium ratio as paleo-temperature and paleo-magnesium reconstructions for the introduction. And then we will go to other calibrations. So the main, the important things to know about these proxies is that before one can use these proxies, It should be calibrated, preferably per species or per family of species, because there is a vital effect, and each species can respond differently to their environmental conditions. And after calibrating, it is important to consider that all of these are measured as the ratio to calcium, and thus they are also vary with the calcium concentrations in seawater. So how do we calibrate a proxy or a new proxy? There are two main methods. The first is by field calibration to collect foraminiferal and to measure their elemental concentrations in the shells and compare it to the measurements of the seawater conditions. And the other method is to do the calibration in the laboratory in culture experiments with live specimens. And this is what I did. So how do we calibrate? First, we need to take foraminiferal live specimens, take them into at least 3 groups and modify the element to calcium ratio of the seawater. And then we can plot the element to calcium in the foraminiferal shells versus the element to calcium in seawater. And the slope of the fit through the data will give us the distribution coefficient. And the definition of a distribution coefficient is the relative affinity for solids in solution, for example, magnesium, to sorb to a surface of the solid, in our case, the calcium carbonate. When the fit is nonlinear, we cannot use the linear regression through the data. We have to use the Freundlich multi-layer adsorption curve, which is a power function. And this is for non-ideal adsorption. Here we have a monolayer adsorption, which is the ideal, and the non-ideal is the multi-layer adsorption. And when we want to calculate the distribution coefficient, we have to use the white tag, which is this equation here, and that represents the slope of the curve. And when the d is constant, like we saw earlier here, then we can use the ratios between the shell and the element to calcium in seawater. So here's an example of a calibration of magnesium to calcium ratios in foraminiferal shells as a function of temperature. On the left, you can see the calibration for deep benthic foraminiferal, and on the right, you can see the planktonic foraminiferal calibrations of many species. And in both cases, the magnesium to calcium in the shell increases non-linearly with temperature. But let's first look at what can we do with an reconstruction based on foraminiferal shells. So here's an example of Delo 18 data that was reconstructed for the past 70 million years for the Cenozoic. And this is a compilation of over 40 deep sea cores, and each data point here represents a measurement of a foraminiferal shell. So you can see that the closer we get to today, there's a larger noise, but it's not really noise. It's glacial interglacial cycles. And this data of the Delo 18 was used to reconstruct best temperature. You can see here in red. And this was done based on this equation here that was developed by Urey and Epstein in the late 40s and 50s. So here we have the temperature that we want to reconstruct, the Delo 18 of the calcium carbonate of the foraminiferal shells, which we measure, and the Delo 18 of seawater, which is used as proxy for ice volumes, but here it is another unknown. So we have one equation with two unknowns, the Delo 18 of seawater and temperature. So when the magnesium to calcium palo temperature proxy was introduced, then it provided a partial solution for this problem of two unknowns. Here we can see an example for a combination of two proxies. Here we have the Delo 18 of the foraminiferal shells for the past 1.5 million years. In the middle panel, you can see the temperature reconstructed from magnesium to calcium ratios. And on the bottom panel, you can see the reconstructed seawater isotopic composition. And this gives us the fluctuations of glacial interglacial cycles. So this is really great and wonderful, but these reconstructions can be only done on short timescales, because when we look further past, the magnesium to calcium ratios in the seawater varied greatly during the geological record. So we have to take it into account. Here you can see the magnesium to calcium ratio as reconstructed from fluid inclusions data mostly. This is the red curve. And in blue, you can see the calcium concentrations for the Phanerozoic. These symbols represent the fluid inclusion data from marine halides. And the variations were very large. If you look at the calcium curve, here we have the concentration of today of 10.3 millimolars. And if we go only 100 million years back or so, then we have 4 times as much calcium. So the variations are very large. Here we have the same basic plot of calcium concentrations versus the Phanerozoic. And here we have a compilation of all the modeled reconstructions based on fluid inclusions data, represented here by the black symbols. And as you can see, each model produced very different reconstruction of calcium concentrations. So we have variations not only in the actual concentrations, but also in the timing.
כן, אני הבנתי.
Okay, sorry. So we also have variations in the timing of increase and decrease in the calcium concentrations. These variations are directly linked to the residence time of each ion in the seawater. So for example, the calcium residence time is very short, it's 1 million years, and the magnesium residence time is 13 million years. So in order to solve this problem of scarce information from fluid inclusions and different models that have different initial assumptions, then we have to get a higher resolution reconstructions in order to know the exact calcium concentrations in the past. So both Yair and David Evans, each one of them individually, came up with the same hypothesis to use sodium to calcium ratios in foraminiferal shells to reconstruct best calcium concentrations for the past 100 million years. The 100 million years is not just a number, it's based on the fact that the residence time of sodium is around 100 million years, and thus it can be assumed as constant. So this is a great idea, but this cannot be validated using field calibrations because both sodium and calcium are conservative elements in the oceans. So that means that the ratio is constant throughout the modern oceans. And this is my part of the research. I did the laboratory culture experiments to calibrate the new sodium to calcium ratio proxy for past calcium concentrations. During these experiments, I also measured other elements like magnesium, lithium, and strontium, and we described their distribution coefficients with varying calcium. And we also tested the effects of other environmental factors like salinity and carbonate chemistry in order to ensure that the use of sodium to calcium ratio is valid. For these calibrations, I used the species Operculina ammonoides from the Gulf of Eilat. This is a high magnesium shallow benthic foraminifera, and we were lucky enough to have Shai Oron that did her PhD under the supervision of Jonathan and Sigal Abramovich, and she cultured these Operculinas during her PhD, and she did most of the collections for my research as well. So thank you very much, Shai, for your contribution to the project. And this species is also an extant relative of the Eocene nummulites that we saw earlier in the Egyptian pyramid, which means calibrating this species can be used to reconstruct based on nummulites, and there's abundant of material to work on. The methods for all the experiments I will introduce now are the collection of operculina from the North Beach in Eilat. All of the specimens were labeled with a fluorescent dye calcine. You can see here in the picture the green fluorescent dye, and this is the old shell. And when we took them out of the calcine and put them into the experimental solutions, then they precipitated new chambers that appear as darker and non-fluorescent. And that means that we could track their growth visually during the experiments. But in addition, we added barium-135 spike to the experimental seawater in order to observe that we actually work on only the newly calcium carbonate shell during the shell analysis. The experiments I will show you today are variable calcium temperature, salinity, and carbonate chemistry. And for each of these, I measured alkalinity depletion, pH, and dissolved oxygen for both the incubation water and the reservoirs. The seawater chemistry was analyzed by ICP-MS and ICP-OES, and the shell chemistry of the foraminiferal was analyzed by laser ablation ICP-MS quadrupole. This was done on the marginal chord. You can see it here. This is the marginal chord, the white bright line around the specimen. And when mounted vertically, we could ablate only the marginal chord, which is the densest part of the shell. And then we have a better measurements. On the right, you can see the barium-135 spike we added. This is a measurement of amphistygina, not operculina, but the principle is the same. When we measure high concentrations of barium, like you see here and here, then we know that we are working on the new shell that was precipitated during the experiment. And when the decrease starts, then we know that we are getting closer to the older shell, and we know to exclude these data points from our calculations. So the first experiment was varying calcium concentrations. I used natural Gulf of Eilat seawater that I diluted to salinity of 35 PSU and added calcium chloride solutions to reach these 4 different concentrations between 11 and 18. And these 4 concentrations were replicated to 3 different temperatures that were kept constant in water baths with simultaneous cooling and heating. All the foraminifera grew well during the experiments. You can see here the growth rate versus the calcium concentrations of experimental solutions, but we did observe an optimum in the intermediate calcium concentrations. We also tried to culture operculina in higher calcium concentrations, but then we got basically no precipitation of new shell, and thus this treatment will not be included in the calibration. And we concluded that the high concentrations of calcium inhibits growth. So here is the main calibration. Here is the sodium to calcium in the shell versus the sodium to calcium in the seawater. And this is the same plot for magnesium. And as you can see, both elements increase with increasing element to calcium in the seawater, but they cannot be fitted with a linear fit. We get a y-axis intercept, which is physically impossible. And then we use the power function, as I described before, of the Freundlich multi-layered absorption curve. And for sodium, we got no change with variations in temperature. For magnesium, we did, but this is well described in the literature, and I'm not going to discuss this today. We also measured lithium and strontium, and for these 2 elements, we have a linear correlation that goes through the origin. And that means that we can still use the power function, but now the age will be equal 1, and then we will get the linear fit. When age is smaller than 1, then we get the curved fit we saw for sodium and magnesium. And then the Y tag, or distribution coefficient, will be constant for the age equals 1, and non-constant for this curve. The variations in the slopes can be seen here. If we put tangents through the curve, then the closest we get to the origin, then the steeper the slope, and that is how we get the decreasing distribution coefficient with increasing sodium to calcium ratios. In addition, we compared our data to other previously published experimental calibrations. Here we have the operculina data for my calibration. This is for sodium, and as you can see, there are not a lot of data for sodium because most papers did not report their sodium measurements. There is one planktonic foraminiferal experiment that was done by Delaney et al., and they varied the sodium concentrations and not the calcium, and they didn't get any change in sodium to calcium ratios. And there is one inorganic calcite experiment by Kitano et al. That can be fitted with a power curve. The same can be done for magnesium, but here we have a lot of information. So let's look just at the magnesium right now. So again, here's the operculina data. This is a high magnesium foraminiferal, but we have lower magnesium contents in other species like Amphistygina, and planktonic foraminifera have a low magnesium content. And in addition, you can see here in crosses and asterisks the inorganic calcite experiments. These were done by Mucci and Morse and Deschutes, Sanchez, and Gonzalez. Mucci and Morse used natural seawater to precipitate their calcite, and Deschutes, Sanchez, and Gonzalez used low ionic strength solutions to simulate cave precipitates. So it was surprising to see that the operculina sits on the same slope, almost the same slope as the lower ionic strength solutions. But even Mucci and Morse slope is closer to the operculina slope than the planktonic foraminifera. So this is something we discussed more in length in the publication we had in EPSL in 2018. So to conclude this experiment, sodium to calcium ratio can be used as proxy for past calcium concentrations. The temperature does not affect sodium to calcium ratios, and lithium, magnesium, and strontium are also well distributed with calcium. And it is important to notice that sodium and magnesium have a non-linear distribution coefficient, which is important when trying to reconstruct for past chemistry of the oceans. The next experiment was varying salinity. Again, I used natural Gulf of Eilat seawater, and I either diluted with deionized water or evaporated the seawater to reach the higher salinities. And when the salinity changes, the element to calcium ratios remain constants for all four treatments. So here is the calibration for the salinity for all four elements: sodium, lithium, magnesium, and strontium. And as you can see here, only the magnesium has a tight fit with increasing salinity. But if you look at the y-axis values, the change is not major. For sodium and lithium, there is a slight increase with increasing salinity, but both fits are statistically insignificant. For the strontium, we observed no change with salinity. So we tried to compare the results of the salinity experiments to the calcium experiments. And here you can see all 4 elements, and on the y-axis it's the relative change in element to calcium in the foraminiferal shells. And I used the calibrations and the values reconstructed for past salinities and calcium concentrations for the past 100 million years. These values are taken from Hay et al. And Siebe and Tyrrell. And in black, you can see the change due to calcium concentrations, and in blue, the change due to salinity. So it's really obvious that the calcium has a much greater effect on the element to calcium ratio for all 4 elements. But salinity have a minor effect for sodium and magnesium, and none for strontium. So we concluded that we can use the sodium to calcium ratios to reconstruct calcium without correcting for salinity. The next set of experiments are carbonate chemistry experiments. So basically, carbonate chemistry includes the pH, the alkalinity, the dissolved inorganic carbon, or DAC, and all the species of carbon in seawater, which includes carbonate, bicarbonate, dissolved CO2, and carbonic acid. But from all of these parameters, only one can be held constant at a time. So that is why we did 2 experiments. The first was constant DAC, and we varied the pH by titrating natural Gulf of Eilat seawater with either HCl or sodium hydroxide. And we reached these values of pHs. And for 2 of these pHs, we also added higher concentrations of calcium by adding calcium chloride solution. So if we look at this figure of the different species of carbon, dissolved carbon in the ocean versus the pH, so here we have the scale of variations we used for this experiment. And when we look at the lower pHs, the 7.4, we have very low concentrations of carbonate and very high concentrations of bicarbonate. And when we increase the pH to 8.6, then we have much higher concentrations of carbonate and lower concentrations of bicarbonate. The second experiment was constant pH, and we modified the DAC by adding sodium bicarbonate to reach these concentrations here. And we adjusted the pH to be constant by the addition of sodium hydroxide or HCl. And if we look at this plot here of alkalinity versus DAC, and we have in red the pH equal lines and in blue the carbonate equal lines. And for this experiment, when we kept the pH constant, then we plotted here, and you can see that all other variables change: alkalinity, DAC, and carbonate ion concentrations. And for the previous experiment I showed, then we kept the DAC constant, and then the pH, the carbonate, and alkalinity changed. So here are the results of the varying pH calibration. So you can see for sodium and lithium here on the top panel, we had a linear increase in element to calcium ratio with increasing pH. The same was observed for strontium. There was no change in lithium, but it is interesting to see the full circles represent the varying pH plus the higher calcium concentrations. And these varied the magnesium and strontium content, but it didn't affect the sodium and lithium. We still need to think about it more, but we assume that because both magnesium and strontium are divalent cations, like calcium, they easily replacing the calcium in the calcium carbonate lattice, and the sodium and lithium are univalent, and thus their incorporation is much more complicated, but further research is needed. For the varying DAC calibration, you can see that all 4 elements varied linearly with increasing DAC. So when we see that both DAC and pH affect elements, then we try to calculate the carbonate ion concentrations using CO2-CIS. And then we can plot both experiments together on the same plot. You can see here with the orange triangles the varying DIC experiment, and in blue circles the varying pH experiment. And for sodium and lithium, all the data falls on the same fit. And for magnesium and strontium, again, you can see that the increasing calcium concentrations affect the magnesium and strontium in a more pronounced way than the carbonate chemistry. But to compare these experiments results to the previous calcium and salinity results, here you can see the same plot I showed you before, but I added the carbonate change in elemental calcium. And as you can see, for sodium, the change with carbonate ion is significant, and thus it needs to be corrected when trying to reconstruct for past calcium concentrations. So to do this correction, this work was done by David Evans, and this is an unpublished paper, and I will show you the reconstructions soon. So he took my calibration of the varying calcium experiment and the calibration of the carbonate chemistry, the two experiments I presented before. And now he plotted it against the omega, the saturation state of calcite, which includes both calcium and carbonate concentrations and a constant. And thus, when if we think about it, when changing the calcium concentrations, then we varied the omega as well. So when correcting for omega, we can see here the corrected sodium to calcium shell versus seawater sodium to calcium ratio. And now we can fit a linear regression through the data and use a constant distribution coefficient. And this is the distribution coefficient that David used in order to reconstruct the past calcium concentrations. He used nummulites between 30 and 60 million years. You can see them, the data for the past calcium concentrations in the blue circles. And they sit really well with the fluid inclusions data. So you can see that we do have higher resolution reconstruction, and we can produce similar results to the fluid inclusion. So this is really positive. And after we reconstruct past calcium concentrations, then we can calculate other elements that have a distribution coefficient with calcium, like we saw earlier for magnesium, strontium, and lithium. So here is an example for the strontium reconstructions. Again, the blue circles are the nummulites data. The black circles are benthic foraminifera, and the orange squares are corals data. These were previously published as strontium to calcium ratios, and David used his calcium reconstructions in order to calculate the strontium concentrations. So this is really exciting to use this multi-proxy. To conclude, sodium to calcium ratios in foraminifera can be used as high-resolution proxy for past calcium concentrations. After we know the calcium concentrations, we can calculate other elements that have a distribution coefficient with calcium, like magnesium, lithium, and strontium, and possibly others. And thus we can get a reconstruction for past ocean chemistry. Because sodium to calcium ratio is insensitive to temperature and salinity, the only correction needed is for carbonate system. And after we reconstruct all the elemental concentrations, then we can use the magnesium to calcium ratio as a paleotemperature proxy and calculate the Delo18 of seawater that can be used to calculate the glaciation and ice volumes in the past. So we get full pictures of the past oceans and past chemistry of the ocean. My research is a part of a bigger project on the sodium to calcium ratio. All of these pictures are part of the project. Sandrine worked on planktonic foraminifera that have a low magnesium content. She did laboratory calibrations in Eilat. She was a postdoc of both Jonathan and Yair. Jolie did her reconstruction for the past 3 million years on planktonic foraminifera, and she's a postdoc of Yair. And Sharon Ram and Matan Yona, they are PhD and MSc students of Jonathan, and they did an additional calibrations of the sodium to calcium proxy on other shelled organisms like corals and sea urchins. And for all of this research, we see very beautiful results and a nice correlation between the sodium and calcium in seawater. So this looks like a promising project, and I'm very lucky to be a part of this. Other people that I did not mention during this talk, but they are part of this project, are Hagit Afek, Wolfgang Miller, and Wei Min Si. And that's it. Thank you for listening, and I hope you have a lot of questions.
Thank you very much, Hagar, for a great defense talk. Jonathan, do you want to handle the questions as well? Are you up for that? Or should I? Oh, you muted. You need to unmute yourself.
Okay, I can do it.
Great.
Okay, so I think the floor is open for questions. So anybody who wants to ask something, please do.
Hagar, can I ask you?
Yeah, of course.
First of all, it was a very nice presentation.
Thank you.
Job well done. And I just wanted to ask you, in your experiment, you said when you reach 26 millimolar of calcium in the seawater,
yeah,
you don't see any calcification going on.
Yeah.
So how come that in the record we see, you know, under high calcium ocean still precipitation? Is it related to other species, or what's the explanation for this apparent contradiction?
It's also other species, but not only calcium varied with time. We have other environmental parameters like the carbonate chemistry, and when you combine the two effects together, it can produce a different response of the foraminifera. And also, these operculina were not adapted to the high concentrations, and maybe in adaptation of millions of years, they can precipitate in higher concentrations of calcium.
Okay.
I would like also to add, perhaps, that in the planktonic foraminifera, they tolerated higher concentrations.
Also
and
for
also the amphistygina that you did and you didn't talk about, they tolerated much higher concentrations.
Up to 30 millimolars. Yeah.
Can I ask a question?
Of course.
Awesome. Yeah. Very nice talk. I really liked it. So do you have any idea where in the crystal lattice does the sodium, is positioned, and how would that reflect on the preservation of this signal? Because sodium is very soluble. We all know that. When you look back at records.
Yeah. So this is still debatable. I don't think there is one answer to these questions. So I think the most recent publications showed that the sodium can substitute for the calcium in the lattice, but then there is a carbonate vacancy, and that means that it's less soluble than in interstitial position, but nothing is certain.
I would like perhaps to add, it's not Hagar's work, but Jiaoli Zhu, who is the postdoc of Yair Rosenthal, she carried a big study on the preservation of the planktonic foraminifera with respect to sodium. And she demonstrated that at least for the past 50 million years, or 40 million years, it seems like the planktonic foraminifera maintain good sodium signal, and she looked at it interstitial water chemistry to demonstrate that, and also for the benthic foraminifera that she also did, they are much better preserved, and there is no change compared to the expected values.
I have a question if there's still time.
Yeah, of course.
So, hi. So, really great work. Thanks for the presentation. So, you showed that you discard the laser ablation data of the old shell. I was just wondering about how well do the pre-experiment elemental ratios, how well do they agree with each other? And basically, because this could serve as an indication of the degree of variability that you expect given organisms grown under similar conditions. Does that make sense?
I'm not sure I got the question.
So the old shells, right? The plateau, say, of barium to calcium or sodium to calcium in the old shells, in the pre-experiment shells, should represent the seawater in which the organisms grew, right?
Yeah. Yeah.
And that seawater is basically the same, maybe with slight variations in temperature. So I was just wondering how similar those pre-experiment ratios were in the organisms that you grew.
There is an entire paper about that that was published by Adam Levy, that is another PhD student of Jonathan, and maybe you can find the answer there. I'm not sure. Or Jonathan, if you want to add anything.
Maybe I will add one word about that. We all know that within the shells of foraminifera, both planktonic and benthic, there is large variation in trace elements when you look at resolution of laser ablation. And if you do this vertical resolution of laser ablation, you really have a resolution of sometimes better than 1 micron, okay? So the record that you see here, which is like 60 microns depth into the shell, you see here at least 70 measurements or something like that, okay? So, and as you can see, the barium is slightly variable, even at the experimental part, but it is also highly variable in the older part. And most known variation is, of course, magnesium. So magnesium-calcium ratio is changing a lot in the shells, and it is together with strontium and other elements. But the important thing is that if you take the whole shell and you dissolve it, you get very reasonable results. And when it comes to sodium, this is work that Yair did with Xiaoli. They looked at benthic foraminifera, they looked at planktonic foraminifera of today and of the last glacial and a bit older, and they all show exactly the same values, species dependent. It does change from one species to the other.
Okay, thank you.
I wanted to ask also something.
Yeah, of course.
Again, it was very, very interesting talk, but I don't understand. Maybe I missed something in the when you show the corrected sodium to calcium, just the last, almost the last, yeah, this one. So when you take the corrected sodium to calcium in the shell, it looks linear, it's nice. But when you measure it, you want to do reconstruction, you don't measure the corrected, you measure the real sodium to calcium. So how do you do the reconstruction? I didn't understand. The past reconstruction, I mean.
Yeah, we use the corrected curve because omega is assumed to be pretty much constant in the past oceans. And when we correct for omega, for a constant omega, then we get the linear fit.
Okay, so you have an assumption there when you go for past reconstruction, you have to apply any assumption.
Yes.
The corrected one for the experiment looks nice, but okay, so I was wondering how you did it for the past, so okay.
Yeah, it's just on the assumption that the omega was pretty much constant.
Okay.
More
Any
questions?
other questions?
Yeah, can I have kind of two questions, I guess.
Okay.
So the first question is that the attempt to do calcium ratios in the past, there was a PhD by Ann Gothman who worked with John Higgins at Princeton.
On corals.
On corals, and she tried to go after uranium calcium ratios.
Yes.
And this was the idea that Broker had, I think, already in Traces in the Sea, that he basically said that you can reconstruct calcium concentrations using uranium calcium in corals. So she has a record out there, I think it was published last year, with, I think, calcium concentrations throughout the Cenozoic. So it'd be really interesting to take your work and David Evans' work and just try and see if those match up. Because both have assumptions, both are calibrating different things, which would be interesting to see if you get the same results. Have you tried that? Is it something that is that on your radar?
I do only the calibrations. The reconstructions are the work of David Evans, and this is not part of my research. So no, I did not compare the two.
Okay, so that I guess then my second question was, okay, so what's happening in the Cenozoic? So we're losing calcium and we're gaining magnesium through time, right? So do you have any thoughts about why the oceans are changing? See, Julie laughing.
I don't know how to start. Well, Jonathan, do you have an answer?
Yeah, perhaps I can say something about that. Hagar's thesis did not deal with the actual variability that occurred in the past, and we were even considering whether to show the results of David at all, just to show you that it can be applied and successfully applied. But the paper that David wrote about this, with all the other authors, of course, was submitted to Science, went through review, and was rejected beautifully. and as a result of mainly of new hypothesis that David put forward, and that is that the calcium is controlling the CO2 in the oceans and in the atmosphere. Okay, and that suggestion or hypothesis was really, I would say, not well accepted by all the reviewers who did a fair review. Okay, so we still have lots of work to do to explain why calcium and magnesium changed in the ocean, but the main result that David received out of this was that the alkalinity and the DIC of the oceans did not change. Okay, of course, he couldn't do it only with his own data, but he used the boron isotope data together with the calcium. And if you make the assumption of constant omega and you have the boron isotope pH, then from constant omega, you can calculate the carbonate ion concentration. And if you have the carbonate ion concentration and the pH, you can calculate the entire carbonate chemistry. And then you can show that basically alkalinity changed very little. DIC changed very little, but PCO2 decreased from 1,500 to maybe 250 or something like that. Okay, and that's why, and that is for a change of about 20 millimolar, of about 10 millimolar in the calcium from the Eocene, where it was around 20 or 23 or 4, all the way to the recent when it is 10.3. Okay, so what is the reason for that? We still don't know, but that is at least a new way of thinking about the entire system.
Interesting. Thanks.
Can I also ask a question?
Of course. Hi, speaker.
Work, Hagar. I really enjoyed it. You compared the errors based on the carbonate salinity and calcium concentrations and how they reflect on sodium to calcium ratios. But it seems to me that you use the slightly different types of variations. So a change in salinity of 5 and a change of carbonate ion concentration of 150 are reasonable in the ocean, but a change of calcium by 20 millimole per kilogram are more than 50 times what you find in the ocean, maybe 100 times the present ocean variation. So isn't it slightly underestimating the error that you get because of salinity and carbonate ion concentration compared to calcium?
All of these values, I didn't just pick a number. I took that from reconstructions for past salinity, past carbonate ion concentrations, and past calcium concentrations from these papers here by Hay et al. For salinity and Sibe and Tyrrell for the carbonate and calcium concentrations.
But even in the ocean today, you would get a range of salinity from 0 to just over 40 with no past variability, just natural conditions today.
Not in the open ocean, but I don't know what to say about that.
I would say, if I may, that in the open ocean, if you are in one station and you go down core, what is the maximum salinity range that you can expect for the past 50 million years? 2 per mil, 3 per mil on one station?
It depends how far you are from a river. If you
that's why I talked about the open ocean. Okay. So this wouldn't apply for coastal waters. But if you go to the open ocean, where Xiaoli is taking all her course, then we don't really have a problem of freshwater input from rivers. That, of course, will change everything. Okay, so obviously, if you go to the Ganges or Brahmaputra deltas, then the story will be completely different. Not only because of salinity, but also because of the trace element chemistry that will change.
Yeah.
Okay, any other questions?
Okay, if not, let's thank Hagar and see you all in the next seminar. Thank you.
Thank you very much for listening.
Thanks.
Bye-bye.
Bye.
Bye.